Welcome everyone to Iron Beetle Show, a show where we take this beautiful open source database implemented in Zeek called TagBeetle and try to understand how it works. And we really go into the deep end of it. We don't draw a lot of pictures. Well, we do draw some pictures, but mostly it's actually going deep into the source code, reading every line, getting confused over what this or that thing does, and figuring that out at the end. And that is quite a useful exercise, at least for me, because TagBeetle is unusual in many things. But one of the things why it is unusual is that it doesn't use any dependencies. It's a database implemented fully from scratch. So if you want to understand everything about how to build a modern distributed database which is capable of recovering from storage faults, you could actually just read all the 100,000 lines of code of TagBeetle, which actually is not that much. I mean, like 50K is like, small project, but like, small production ready project, and like 100K is like, well, twice as much as that. That's like, not millions lines of code. I mean, we've actually read most of it, and it took only like 70 episodes, so 70 hours, so it's not huge time investment. So anyway, you could read all that, and you understand everything there is to write in a database. And we've actually did most of the things. So for our latest arc in our journey, we are looking at the Whopper. The famous, okay, we are looking at the Whopper. Well, I'm looking at the Whopper, but you aren't. And okay, yeah. So now you're looking at the Whopper as well. So the idea here is that we want to test our system. And we want to test it really reliably. We want to test it exhaustively. We don't want to rely on unit tests, mocks, or whatever. We kind of really want a high level of assurance that we don't have critical bugs. So the idea is that we run our system in a simulator using a randomized workflow. So we take this whole cluster of 6 nodes, and then we treat them as logical state machine. And we put all 6 machines into a single thread and run it in our deterministic simulator. I think we've covered most of the things about the simulator, except the one. we haven't yet covered how we actually generate workload. So, okay, kind of like the rough idea is clear. Like, we want to generate random transfers, but how do we check the results are correct? And this is what we are going to look at today. And surprise. So I think, if I'm not mistaken, tomorrow there is going to be some huge reveal on our blog post. Like, I mean, on targetmiddle.com/blog. So if you are watching this live, that's like a bit of a teaser for that. If you are watching this in recorded on YouTube, well, too bad, but well, you can now check this announcement. But basically, what I'm going to tell today is actually pretty relevant to that next thing. Okay, so that's the plan for today. To understand how we generate the workload, how we decide which specific random transfers we want to do, and how we check that the results are correct. Okay, and this is going to be hugely painful because this is the part, oh dear. So I guess if you paid attention to my super small console font, you also get an earlier review there, but well, I guess it's fine. It's fine now. If you haven't noticed it, that's fine. You will learn tomorrow. Okay. So like, this is a part of Target Middle which I personally understand on a very superficial level. I tried to read it, like, 5 times, and like every time it was like hugely complicated. I haven't built a good mental model. So we'll just try to plow through, and well, maybe we do, maybe we'll don't. I mean, you need to try to figure this out. Okay, so let's go to our Whopper, our main loop, where we step through this virtual state machine, and then in the visibility tick, you see that there is this tick requests method. So presumably this is where we actually drive our random inputs to the state machine. So let's see, what do we do here? Well, there is that pattern which we've seen a couple of times already, where we randomly flip between 2 modes, like either we send in requests or not send in requests. If we are not sending requests, well, we are not sending requests. Otherwise, I guess we checked whether we have sent all the requests that we wanted, so no more requests. Then we just flip a coin and decide whether we need to do a request on this tick. And next. So next we pick a random client who was not evicted. Okay, so this is our client. Then the messages aren't added to the reply sequence until a reply arrives. Before sending a new message, make sure that there will be definitely a room for it. So, okay, so apparently we are storing a reply somewhere, and we need to make sure that we have a room. Okay, yeah, so we just basically compute the in-flight messages. Okay, so if we have room for this message and we are not currently sending a message, then we do a request. And here we get like the tricky part, like how do we build requests? And this, I mean, they got behind this like simulator workload field request thing is like it is scary. I'd rather do compaction episode once more than go to workload, but well, this code is written, so you gotta understand it. Okay, but anyway, so for now let's ignore it and let's see what happens there. So then we do a request, and presumably in the cluster we have on-client reply. So what is on-client reply? Okay, so this is callback for the cluster. So okay, we are setting it up here. Okay, this is curious. I would expect that like when we receive a reply to our request, we trigger some kind of a check, but that's not happening. Maybe this happens inside the cluster on client reply, client on reply. Okay. Okay, I don't really understand how this works. So we should be doing something here. Okay, so reply sequence. We have a reply sequence. So presumably reply sequence is where we get the replies. So who inserts? Oh, there is on cluster reply. So what is on cluster reply? On cluster reply. So it is also a callback inside the cluster. And okay, so okay, that now makes sense. So like we could listen for actual reply messages, but you know, with our simulated network, the reply can get lost. So there's no guarantee that we'll get like all the replies. And presumably for state check-in, it would actually help to observe every single reply. And that's why we use an internal hook inside the replica to observe this. So if we go to the replica, we see that there is an event callback. So when you initialize a replica, you pass it event callback. And in the main, is it nullable? Yeah, it is nullable. So in the main, we don't pass event callback. It's null. But in our cluster, we pass this callback. And then if we go in the replica, at some key points, we invoke this callback, and in particular, yeah, so when we execute something, we say, hey, now we have executed, this is the prepare that we executed, and this is the reply that we are executed. So that is how we get here, where we have committed, and here we do on cluster reply, which is a cluster level callback, which is on cluster reply. So we insert simulator into the reply sequence. And then if we see that we generated next reply, we do some basic checks there. And call workload on reply. So, okay, again, when reading code, it's useful to read it like top down. So we kind of like see that when we are sending a request, we use like this build request, and then we are receiving a reply. We call this on reply. So build request and on reply is presumably the secret sauce of the workload. Okay, workload. It should be simple. 2,000 lines of code. Well, that doesn't look simple. Like just for comparison, cluster is 1,000 lines of code. So apparently our workload is actually more complicated than like the entire code to orchestrate the cluster itself. Yeah. Okay, let's see how big of a dent can we make today in this giant file. Okay, before we dive in, let's see how we actually create workload. So we create workload inside our simulator, and we pass workload options. And I've seen this, that we also generate workload options themselves. So it is also like this fast test. Okay. Workload init. Otherwise, okay, we pass the options, we pass random number generator, we pass allocator. Nothing particularly eliminated. Okay, I guess it makes sense to start with workload options to understand what we are even doing. Okay, and okay, wait. Options. Why options itself is parameterized? Workload options. Wait, state machine workload options. So actually workload lives on the state machine, and so workload type. Okay, so this is workload type, and options should be here. Okay, so action lookup. Okay, there is a bunch of okay, so actions is like basically state machine operations. Lookups is, I don't understand what it is. Query transfer that has either been committed or rejected. Query transfer whose create transfers is in flight. Okay. Okay, well, let's just roll with it. Option stack. Okay. Batch size limit. It's pretty clear, like how many items how many individual transfers do we plug into individual message? Multi-batch pure request limit. Well, that has to do with automatic batching, which I think we haven't covered yet. So let's do that here. Auto batching. It is ensuring that our to-do list grows faster than we are, grows faster than it shrinks. Okay, auditor options. Okay, so apparently we have something called auditor, which also has options. Transfer ID permutation. Well, this is apparently like something we can use to generate IDs and kind of like decode it, because I mean, so I think the reason why we need it is this, like our IDs are random, but we actually want to kind of like understand that, hey, this was the first transfer, the second transfer, the third transfer, etc., etc. So we could say that, hey, okay, let's just use IDs 1 to 3, but well, maybe that will uncover some, well, not uncover some tricky parts in our state machine. So we kind of like use different mapping functions which allow us to get from indexes to IDs. Okay. Okay, that makes sense. Okay, then we have two sets of fields which feels like they mean the same. So this gives weights for relative weights for operations, like how frequently do we create transfers, how frequently we do like create accounts. But this is, oh, okay, this is probabilities for operations being invalid in a different way. Okay, yeah, so, okay, no, this is not duplicated. So here we pick an action randomly, and here we additionally maybe flip a coin and corrupt an action. Because again, negative space is important. You should not only test the happy case, but you should test the happy case, the sad case, and you should be able to exactly trace the boundary between the happy case and the bad case. Okay. So different probabilities. Okay, so that like this kind of like looks reasonable. So basically, just a bunch of probabilistic distributions. Because again, as this particular blog post shows, oh dear, I realized that I am not using dark theme. Okay, that should be easier on your eyes. Sorry for that. Okay, so as this blog post shows, what you want to do is that not only you want to generate the actions randomly, you actually want to pick a random distribution of probabilities to generate the actions with. Okay. So how do we generate options? So we take random number generator, we take parameters of our whatever simulator run, and then we pick up the limits, pick up the random way to encode indexes into IDs, and basically pick everything else at random as well, which is actually, I mean, this is not exactly swarm testing. We should be allowing zero probabilities. Okay. Whole bunch of different probabilities. Okay, that's relatively tame. Let's see what does initializing workload entails. So we have this generation probabilities. We have our allocator. We do something with the auditor. So judging by the name auditor is a thing which will be validating our replies. So let's try to ignore this for now. Well, actually no. Before we go into the init, let's actually see what are the fields we are storing, because as usual, whenever you read the code, not only you want to read it top down, but you also want to start with the data you want to start with the tables first. Okay. So we have PRNG, we have auditor, we have options, we have transfer plan seed. I guess we generating transfer plans at random, and for some reason, well, probably we need to be like at the end we want to regenerate them, and that's why we kind of like freeze the state of PRNG here, presumably. So, and we have okay, so we have a set of in-flight transfers. Okay, transfer batch queue is just a priority queue of transfer batch. Well, a transfer batch is pair of indexes. But where are the transfers? Like, are they part of the auditor perhaps? What fields do you have, dear account auditor? Well, huh. Okay, this is mysterious. So I don't, so like, in my mental model, the way this should work is that we generate a bunch of transfers up front, but we don't. Okay. Well, let's see what we do here. So we initialize auditor, we initialize this queue. Then for each account, okay, so I think auditor at least stores accounts. Well, let's see. Okay, let's put a pin on this, but I was hoping that we can get away without looking at the auditor just yet, but well, apparently we have to look at the auditor. So, oh, actually we do initialize, so auditor stores accounts, but we initialize it here. Let's just double check that. Auditors, they need just yeah, so accounts are undefined here. Okay. It's okay. This I don't like this. So you know, like we kind of like initialized auditor, but actually accounts are not initialized, so we need to initialize it here. That's kind of like yeah. But, well, okay. Auditor query intersections. What is a query intersection? Okay, I have no idea what's that. Oh, okay. Ledger 1. Kind of like feels weird that we always create accounts with Ledger 1. Well, okay, anyway. So I guess the main thing is that how do we get account ID, and well, yeah, we use pure mutation for that, which makes sense. So okay, let's maybe just like quickly look at this encode method just to understand how we do this. So permutation is either identity, inversion, zigzag, random. When we encode a number as an identity, we return number. If we encode inversion, we kind of like invert that. Well, subtract from 128. If it is zigzag, we like, you know, do even odd. And random, we okay. So I think we are like we should be starting with data in the middle. And I think we do. So like random bits. Random mask. Okay, I don't really get it. Okay, let's see. So yeah, it says that we should. So basically, like random bits should select a U64 in the middle of a U128, and I don't. Oh, okay, I see. Okay, I see it. Yeah. I think we only allow 32 bits for data. So well, no, it's still kind of like doesn't make sense. So basically, okay. So oh, okay. So okay, this is actually super simple, but I'm super stupid. Okay, so let's see this. Max int U64. It's basically like f f f f f f and twice as much, and then we shift that by 32. So we get 1, 1, 1. And like, I mean, this is like a 128-bit number. So this is actually our mask. And then we invert it. So actually, this thing turns into zeros. Okay, I'm lost here. Well, if I were using VI, that would have been much slower because I actually don't know how to use VI efficiently. But okay, so basically we get this mask, then we end it with random numbers. So these Fs here turn into uniformly random bits. Middle is zeros, and then we fill middle with the data, and then we unpack it. Okay, so that's basically it for ID permutation. Super simple data structure. Okay, where we were? We were in the auditor, so account to index ID, and that was in the workload in it. So yeah, basically just generate account with like IDs which look quote random, but actually where we could decode this ID into index. We always use ledger one. That's not great, I think. Okay, so then we flags, and this, I mean, this, okay, this. This is kind of like, I mean, what if we haven't considered all the flags here? Should we? Maybe. Yeah, I don't know. Okay, transit errors. It's kind of like still. I'm still curious how we actually build request. Okay, let's just see like build request. How we actually build a request. Okay. Okay, so presumably the first request we ever do is that we create accounts. Otherwise, we pick a random action, which I guess might be create accounts. Let's see, when we say that create accounts. Okay, yeah, so we definitely create some accounts at the start, but actually we might create more accounts later. Okay, so we get an operation which we want to create. We compute like the size of the whole batch. Oh, and then we have this multi-batching, which I really wanted to avoid. So let's kind of like gloss this over. So I guess build request batch is where we actually do this. Okay, so we have action. Which is okay, yeah. So basically we dispatch actions and we have this. So create account, create transfers. Okay, let's see. Let's see create accounts. How do we build that? Okay, auditor expects create accounts. So so presumably we in flight queue. Okay, so presumably first we notify the auditor that, hey, we are going to be creating accounts, so please reserve some space for the results. Aha, this is okay. So again, as a kind of like suspense or maybe early warning. So like, please pay attention to what is happening here, because this is like what we're trying to do here. You see, I think, so we are generating the request. And when we're generating the request, we immediately try to fill the result that we expect to see, if I understand the code correctly. Okay, so we pick a random account. We say that, hey, this is account, and we expect that like everything to be 0. And then wait, okay. Wait, I don't understand. Oh, okay. Wait. Okay, maybe I'm wrong here. So accounts is actually like our request body. So this is what we're going to be sending to the remote cluster. So we are essentially copying. So this is our request. Okay, so no, this is not a result. This is a request. This is a result. And we say that the result is going to be, what is account result set? Enum set tb create account result. Okay, so this is presumably the set of expected results. And originally we say that, hey, we don't expect anything. So then we flip a coin and we say that, hey, account ledger is 0. And okay, yeah, and now we see. So I was right to say that we generate results up front. I was wrong at specific place where we do. So but this is not the result. This is a request, but this is the result. So we flip a coin, and if we create an invalid account, we say that either we expect to get exists with different ledger, or we expect to get ledger must not be 0. Okay. If this account was created, then if this account was not created, we expect to see okay. And we always expect to see exists because this account might be reached with something else. Okay. So that is pretty tame. Actually, let's check on reply, like the matching on reply for accounts. What we do for accounts. Okay, I assume that somewhere here there is always also going to be like a similar dispatch. Okay, this is it. So then we say auditor on create accounts. Okay, so this is where we are creating a batch of accounts. Here we got the response from the cluster, and we want to understand whether that response was correct. And I guess we want to verify it via this result set. So this is our response, and somewhere inside the auditor, there should be a set of expected responses. Okay, so we take an in-flight request, which we expect to be in flight. And then we iterate all the results. And yes, indeed, we check whether the expected result set contains the actual result we have observed. And then if the account was created successfully, we say that, hey, now this account is actually created. So what's account state? Created. Okay, so some account state. And then some stuff about query intersections, which looks complicated, but probably there shouldn't be any bugs around query intersections, right? Can't be anything wrong there. Okay, so that's actually relatively tame. Okay, I guess, like, I bet there are like harder parts to this auditor, and the first 5 times I tried to read it, I hit the harder parts, but now that I'm trying to nicely explain it, actually, I mean, I now see like the thread. I now see the plot, which is not what I would have expected. It is getting much better. Okay, so let's see how we create transfers. Okay, so hopefully here you will get lost because it should be more complicated. Okay, but maybe I'm wrong. Okay, so first, the same thing. We notify the auditor that we are going to create a transfer, and that returns us a result set, which presumably we will be filling with the expected return codes for creating transfers. Okay. So then we have transfer index to plan and transfer index to ID. Well, transfer index to ID, I bet it's simple. Yeah, it is simple. So we do the same like permutation thingy. And then we do build transfer, and there is also this thing called transfer index plan. Okay, so what is transfer index plan? It is some random plan. Okay, what is a transfer plan? A transfer generated from the plan is guaranteed to have a matching outcome, but it may use a different method. For example, method pending may fall back to method single phase if the auditor's pending transfer queue is full. Okay, so here we are trying to plan our expenses, I think. Okay, well, we're generating budget transfer. Whether it is limited transfer and where it's a single phase pending. Okay. Outcome. Success, failure, unknown. So if the transfer plan is not valid, then we expect failure. If limit, it is unknown, so the transfer might or might not succeed. So if it is valid and is not limited, then if it is single phase and pending, it is always success. Otherwise, it is unknown. Well, because if you post or avoid a pending transfer, presumably it could be the case that either the transfer you're trying to post or void doesn't exist, or that it already has been posted or voided before. Okay, doesn't look as scary as you thought. Okay, so build transfer. The transfer build is guaranteed to match the transfer's planned outcome. The transfer build is not guaranteed to match transfer's plan method. Okay. And this presumably returns. This is complicated. This presumably returns the actual possible outcome of this thing. Okay. If a specified method is unavailable, swap it. Change the method may narrow the transfer outcome from unknown to success or from unknown to failure, but never broaden it from success to unknown, from success to failure. Okay, lattices. Lattices are everywhere. Please learn algebra. Okay. So if a method is pending, okay, so this is the narrowing. So if the method is pending and we reach the limit of pending transfers, we like downgrade this to single phase. Similarly, if we want to post or void, but there isn't any pending transfers in flight, we also downgrade this to single phase. Okay. Index methods. Transfer templates, index valid, index limit, index. Okay, so now we are finally coming to that part where like I know it's like complicated, because what is a transfer template? Transfer template is a giant table. It's a giant table of what? It's table of template. Template is a struct. No, template is a function. We should turn transfer template. So what is transfer template? Is the ledger and the result set. So what is the result? The result is, okay, the result is a set of results. Okay, so this number is ledger. So what is 0, 0? It is invalid and unlimited. So invalid, unlimited, single. We create against ledger 0 because it is invalid, and we expect ledger must not be 0. Okay. Then the same thing. Post. Okay. Now, limited transfer, but still invalid. So we still have like the ledger problem. Okay, now valid and unlimited. Valid and unlimited. Okay. Otherwise, two-phase awk. And two-phase awk is that, okay, either it is awk or already voided or already posted or expired. Okay, and finally, oh dear, this reads pretty much like functional programming. Like you don't usually read Zig like functional programming. Well, it is, and it's as any functional programming, it's like impossible to understand what's going on here. It is possible to understand what's going on in functional programs. I wrote a bunch of like Haskell code, Clojure code, SML code, a tiny bit of a camel, a super tiny bit of F#, a lot of Emacs Lisp back in the day, but still, if I try, I can read it, but I need to expand actual effort when trying to get through abstractions. While with imperative code, I don't feel like I'm reading code. Yeah, I guess that's it. When I read imperative code, it's like reading in my native language, Russian, or in a language which I'm like very familiar with, like English. You just like you absorb the information. You don't perceive the act of reading. While reading functional code feels like reading in a foreign language which you're not super familiar with. Like for me, it would be like Portuguese, where you actually spend, depending on the level of knowledge, either a little bit of your mental effort, of your conscious mental effort, or a lot of your conscious mental effort on actually just the raw process of reading, like parsing the words, parsing the grammar, and like understanding what it means. Like you don't like perceive the meaning directly. So anyway, so either it's like set union. So basically limits, okay, exits debits, exits credits, true. Like really, this either, it would have been like simpler to just say, okay, just list them. Okay, anyway. So basically, this thing sets the ledger. And I don't know why we do 9 here rather than 0. Well, okay. Sets the ledger, and that's it. Okay. Transfer template. Woohoo! We get transfer template. Okay, transfer plan limit. So if we limit something, we limit either debits or credits or both, and then we pick account. Okay, so presumably, like, oh, okay, I get some glimpses of what we are doing here. So, like, we kind of like, we set our mind to generate a transfer, and we set our mind to generate a transfer which might hit credit or debit limits. Okay. After we decided that, we actually need to pick accounts which have limits enabled. So this is where we do this pick account. Okay, so we kind of like, we basically pass a bunch of predicates here. Okay, so we go through our accounts, which we initialized. And by the way, how did we initialized? Okay, yeah, we randomly initialize the accounts with debit credit. Well, okay, let's see. Okay, so we basically pick like, we look linearly through accounts and pick the first one which matches our filters, but we start this linear lookup from a random offset, so we actually pick a random account which matches this. Okay. What is this? Oh, okay. This is just bad. Just bad Zig formatter, because it really should be something like this, or I don't know, maybe something like, or something like this. Like, I mean, it's like, yeah, well, nothing is perfect. Zig formatter is not perfect either. Okay. So what is account filter? Well, okay, this is not okay. Let's improvise. So that was like for queries. I mean, there can't be any bug with queries. So let's look at the create accounts, create transfers. Okay, so we pick account which exists, and which satisfies our limit flag. Of course, we might not, it might be the case that we don't find this account, and in this case we return null, so like we can't create this transfer. And if we cannot create this transfer, we actually save it here. We aren't going to create any more transfers. Okay. Same goes for create accounts. Query intersections. Oh dear, that is the query stuff. I guess I won't be explaining how we fast queries until we learn how we actually execute queries, which we should hopefully switch to soon. Do we have queries in our to-do? Queries, okay. Actually, we probably should go to queries after Whopper, because I feel that like queries is at least something I'm personally interested in learning. Okay, and then we make transfer. Okay, we say this from this account to this account. Some flags and some amount of up to 256 things. Okay, then we set pending posted, post pending avoided. Okay, so the problem here is that I think we've went through like half of auditor, and I'm like, we are at an hour, and I'm feeling like my mind is melting. So let's do this. Bear with me. We'll finish understanding these create account functions, but we won't be looking at the auditor side of things, like how we validate that the account is valid, until next week. So we won't be starting with query next week. That would be a little bit later. Okay. So pending. If we want to generate a pending transfer, then we set a pending flag and we set some timeout, which is random, but presumably not too high. Okay, if we want to post a void, then we want to find, well, a pending transfer to post a void and set this. Okay. Okay, and that's it. So okay, I guess let's stop here. That's kind of like in the middle of things, but well, I mean, let's finish it next week. So there we go. We've started looking at the way we generate random data to throw at our cluster. And one curious thing here is that our generator is actually highly structured. So you see, like, we actually don't, like, I mean, I describe this as like we generate random transfers. That's not what actually is happening. We are always very intentional about our generation. That we kind of like, we first plan and we compute upfront the result we want to get out of our execution. So we kind of like say, okay, like I do this and I expect this to like succeed, or I expect this to fail, or I expect this to fail or succeed. But if it fails like with this particular error, or this particular set of errors. And then we look at the data we have and we try to generate transfers which make our predictions true, which actually is pretty hard thing to do if you think about it, because we don't have super tight guarantees on like in which order our requests will be generated. That's why, like, you know, we try hard to predict the result, but sometimes it is just unknown because we don't know whether the thing will succeed or not. Okay, that's it for today. If you watched this live on Twitch, then you've seen a bunch of spoilers today. Like, I mean, it's a giant amount of spoilers, so you probably are guessing what's coming soon to Target. But if you don't, then you should be not reading our blog post for a while, at least until this video is published on YouTube, and then you should watch this video on YouTube, at which point you could also enjoy this suspense. Okay, thanks for watching, and see you next week at 5 p.m. UTC, live on Twitch, and slightly later than on YouTube in the recording. Goodbye.